Hello. Today we're going to talk about using quantitative information from balanced equations. You know this as stoichiometry, I think. So here we have a chemical equation. It is 2 hydrogen plus 1 oxygen makes 2 water molecules. Let's talk about how we can interpret this equation briefly. One way is a molecular interpretation. This 2 means we have 2 molecules of hydrogen. This absent 1 means we have 1 molecule of oxygen making 2 molecules of water. So one way to interpret a chemical equation, a balanced chemical equation, is on the molecular level. 2 molecules of hydrogen combined with 1 molecule of oxygen to make 2 molecules of water. Now, another way to interpret this equation is on the mole level. And that is because, let's consider, we have this equation. If we were to multiply each term by 6 times 10 to the 23rd, we can do that because we're multiplying each term by the same thing. We're multiplying each term by 6 times 10 to the 23rd, so it's proportional. And another word for the number 6 times 10 to the 23rd is mole. That's a mole. So if we multiply these molecules by a mole, then we can also interpret this equation on the mole level. So this coefficient of 2 also means 2 moles of hydrogen, either 2 molecules or 2 moles. We can read it either way. This absent 1 means 1 mole of oxygen when we're interpreting it on the mole level. And this 2 means 2 moles of water. We know from last year that we can convert moles to grams. The mole is a counting number. The gram is a mass number. 2 moles of hydrogen is the same thing as 4 grams of hydrogen. We know that it's the same thing because they're proportional. If one mole of hydrogen has a mass of 2.02 grams. You can find that on the periodic table, and that is going to be proportional to the mass of 2 moles, which will end up being 4.04 grams. We didn't know this at first, but I did this math down here. I cross-multiplied. 2 moles of hydrogen times the molar mass equals 4.404 grams. So 2 moles is equivalent to 4 grams of hydrogen. 1 mole of oxygen in the same way will be equivalent to 32 grams of oxygen. And notice the conservation of mass here. Let's draw an arrow down here. 4 plus 32 is 36. So that the mass of all of the reactants is equal to the mass of the products. So this is on the mass level. We can also interpret a reaction on the mass level if we interpret the mass of all of the reactants and all of the products together. We will be interpreting equations quantitatively like this all year long. So let's start. Okay, we have a question here. Determine how many grams of water are produced in the oxidation of 1 gram of glucose. And I want to talk about vocabulary for a second. This says the oxidation of glucose, because we're combining with oxygen. We're going to talk more about oxidation reactions in our next unit. But this is also what type of reaction? I'll pause. It is a combustion reaction. It's combustion reactions are oxidation reactions. All combustion reactions are oxidation reactions. Not all oxidation reactions are combustion reactions. We'll talk about that more later. But as we discussed in class when Brandon asked the question, anytime you combine oxygen with something, you have a combustion reaction. So we're going to find out I'm going to circle it, how many grams of water are produced from 1 gram of glucose. I always circle in my questions what I'm looking for. That's very, very important because we work backwards, and what I'm starting with. I want to introduce to you a way to keep track of these type of problems because this method, called a BCA table, before, change, and after, is going to be very helpful for limiting reactants and really helpful for equilibrium. We'll give it a different name in equilibrium, but it's the same thing. So we're going to keep track of our moles in a before, change, and after table. we only put moles. Only mole amounts are recorded in a BCA table. So we need to convert our 1 gram of glucose into moles so we can record here how many moles of glucose we have before it starts reacting. So let's do that. So I'm going to take I'm not writing this as a proportion, although I could. I took my 1 gram of glucose, I multiplied it by a conversion factor. For every 1 mole of glucose you have, it weighs 180, it has a mass of 180 grams. So every mole of glucose has a mass of 180 grams. I write it in a way that my grams will cancel. And this is how many moles of glucose that is. Now, because we had 3 significant figures here, I actually have 4 here. I'm keeping 1 extra one until the end. This is my moles of glucose. I'm going to write that in my before section here. Before the reaction starts, I have let's do it in red, 0.0055556 moles of glucose. That's before the reaction starts. Before the reaction starts, I have 0 moles of carbon dioxide, and I have 0 moles of water because they haven't reacted yet. Now, let's look here at how many moles of oxygen we're going to need to react with this 0.00556 moles of glucose. Here we're going to have to do a little side math. For every 1 mole of glucose that we have, we need 6 moles of oxygen to react. So for every 1 mole of glucose we have, we need 6 moles of oxygen. So I'm going to use that ratio to figure out how many moles of oxygen I need if I have 0.0056. It really is a proportion. We need 6 moles of oxygen for every 1 mole of glucose. And so therefore, if we don't have 1 mole of if we have 0.0056 moles of glucose, how many moles of oxygen do we need? That is a proportion. I can cross-multiply and solve it the way we typically do in class. We would take the 0.00556 moles of glucose that we have and multiply it by this conversion ratio, 1 mole of glucose over 6 moles of O2, and therefore we will need how many moles of oxygen? Hopefully you caught this mistake. I wrote this backwards. Oh, darn it. The numerator has to be the 6 moles of oxygen, and the denominator is the 1 mole of C6H12O6. And then if we multiply, these will cancel, and we will need 0.03336 moles of O2, which I'll scribble in here. Okay, so those are moles of O2 that we need. You can see the number is much larger than the number of moles of glucose we need because it's in a 6-to-1 ratio. 6-to-1, 6-to-1. Our change, we're going to use up all of our reactants. So our change here, I'm going to use all of this up, 0.005556. I have a minus sign in front because it's going away. And after the reaction, I'll have no glucose left. I'm going to use up all of my moles of oxygen because so there's a minus 0.03336, and after the reaction, I will have 0 left. Now we need to consider what is our change for our products. Let's look at our problem and look at our ratios. For every 6 moles of oxygen that we use up, we make 6 moles of carbon dioxide. So the moles of carbon dioxide that we make will be equal in number to the moles of oxygen that we used. Well, we're using up 0.03336 moles of oxygen, which means we will create, I didn't leave enough room to write, 0.03336 moles of carbon dioxide. And similarly, for every 6 moles of carbon dioxide that for every 6 moles of oxygen that we use up, we will create 6 moles of water. So the number of moles of water we create are equal to the number of moles of oxygen. So we will create 0.03333 moles of water. And that's what we'll write down here, 0.0333336 moles of CO2 and 0.03336 moles of H2O. At this point, we go back to our question and we see what were we asked to find. And we were asked to find how many grams of water. Well, we know how many moles of water, that's what these 0.033336 moles of water were created. We can now convert those moles into grams. I'm going to make this smaller and then do that in my extra space. Oh, darn it. So we'll squish that in, we'll move that up. Go away. Okay. So, to finish this up quickly, I'm going to take my 0.0333336 moles of H2O, and I will multiply that by a conversion factor from moles to grams, something that shows that for every 1 mole of H2O, I have 18 grams of mass. Every 1 mole of H2O has a mass of 18 grams. That will help me figure out the mass of 0.0333336 moles of H2O. And we will make 0.600 grams of water when we start with 1 gram of glucose.